handed up a little bit of break, and we are ready for the third speech of the day. So welcome on our stage to Piotr Skalski, who is open source lead in RoboFlow, and he is very active online in his divulgative posts on computer vision. So, Piotr, thank you very much and enjoy the stage.
Thank you. Okay, just making sure you hear me, yeah? That works. Cool. Okay, and the presentation is there. Perfect. Okay, so yeah, my name is Peter, or Piotr in Polish, and I'm open source lead at RoboFlow, as you heard. We are a US-based computer vision company. We help our customers do labeling. We help them train models in the platform. We develop our own architectures of models. And we help them deploy those models, whether or not in the cloud or on the edge devices, even if that edge device is on your forehead, that we can do that as well. For the, ooh, that's not good. That's not good, because my whole presentation is pretty much videos, guys. So if the videos will not run, that's a problem. We'll see. Cool, okay, it works. It worked. Okay, so for the past year or so, we do more and more like computer vision and robotics stuff. So here is like a demo rig that showcases using robotics and computer vision to detect defects when you manufacture PCB boards. And yeah, we use like cameras with crazy lenses to zoom out really close and look at every transistor, whether or not it's there, whether or not it's properly installed, stuff like this. And yeah, we have quite large customers, mostly in manufacturing industry. So that's what we do. What I do at RoboFlow is open source. Yeah, so I have several. Company have several open source projects. Collectively, I guess like around 70,000 stars on GitHub in the 4 years across a few of them. What I do also is build demos. And I share them online. And those demos are pretty much things that I build to show people that don't use computer vision, how they can leverage computer vision to solve like real life problems. This one is created a few years ago. It's pretty much a combination of like deep learning and traditional computer vision to be able to estimate the speed of moving cars and visualize them in 3D. I wrote that visualization before cloud code was a thing, so I'm pretty proud of that. And I also used to play basketball. I generally like sports like soccer, football, things like this. I'm football and we're in Italy. So at some point I was like, hey, maybe I can kind of like combine those two things. Maybe I can build demos, but use sports as this kind of like sandbox where I will test different computer vision models in sports. Sports is actually pretty hard. It's like, every second matters, every centimeters matters. Like sometimes a fraction of a second can decide whether or not the team will win World Cup or NBA finals or stuff like this. So if you will make computer vision solution work in sports, there is a big chance it will work in other domains as well, because this one is very competitive. And this particular tag is the story of a demo that I built. It's called Basketball AI. If you want to learn more about that, you can scan the QR code. There will be a lot of QR codes in this presentation, I can tell you that already. The code is open source, the models are open source. That's what we do. We try to open source almost anything that we can, at least in my team. So there's that. Okay, so before we'll dive like super deep into this project, let me just peel back the layers and show you what models kind of we'll use and what tasks that we'll try to attempt. So the baseline for this whole project is object detection. We trained RFD-TR to detect different classes, most importantly players, and more about RFD-TR in just a second. We'll use those players to prompt segment anything free model to acquire track information along with masks. Then we'll use those masks to cluster those players into teams. will try to understand the surroundings around the players to detect like characteristic points on the basketball court, and then use all of that to, first of all, recognize them, so attached names to those players, and also locate them on the court. We'll do a little bit more advanced stats as well, so we will try to recognize if the player is shooting the ball, where in particular that player is shooting the ball, and the outcome of that shot as well. And we'll also try to acquire like accurate information about the movement of the player. Those of you who know anything about professional basketball, it's pretty much memorizing plays and executing them efficiently when the time comes. Like coaches literally pick plays to take leverage of some weak sides of the opposing team. So knowing which play is being run is actually very useful information. Okay, so let's start with picking the right detector. As I told you before, we used RFDTR, which is transformer-based open source detector that is state-of-the-art both when it comes to accuracy and speed. And like I said, it's open source, like really open source. It's Apache 2 license, contrary to other models that are on that list. And what you see over here is Coco benchmark. I will tell you a little bit more about Coco in just a second, but in that chart where you would like to be is in the top left corner. That means that your model is super fast and extremely accurate. So the closer you can be to top left corner, the better. So like I told you, the model is pre-trained on Coco dataset, and Francesco, I think, is not here, but he used to work at RoboFlow. And when he was there, he co-authored a blog post called What the Fuck Coco? And the name is there for a reason. So the Coco dataset have some problems. First of all, Microsoft released it in 2014. The data was collected in 2012. So the problem is that world has changed since then. 2012 was a few years after the iPhone got released, I think. And back then, a lot of people still used those phones with keyboards. So what happens right now, same goes for displays, you know, we use flat displays right now. So what happens right now, if you will pre-train your model on Coco dataset and then show it like a phone or a new display, it will, phone will be, I don't know, remote control, for example. The other thing is like distribution of the classes in this dataset. In theory, has 80 classes. Those are like people, car, things like this. So it's 135,000 images. But there is, for example, a class called hairdryer, and it's only on 200 images. So it's less than 1,000th of a data set, which creates a massive class imbalance. So realistically speaking, those models don't really detect 80 classes. If you would show hairdryer to the model, by the way, who choose like hairdryer for like 80 classes that you can choose in the world, you choose hairdryer, it's pretty crazy. Yeah, speaking of crazy things, yeah, I spent maybe 2 minutes browsing through the Coco dataset, and I already found this guy with stuff attached to his body. There's also like crazy amount of like public toilets there, which is interesting because public toilet is not one of those 80 classes. But Microsoft collaborated with universities to crowdsource and crowd annotated that data, so I assume this is kind of like the sense of humor you get when you are 18 or something like this. So there's that. So ultimately, what I want to say to you is we don't really care that we are a state-of-the-art on Coco dataset because it doesn't really matter. Anybody who do anything with those models, they usually fine-tune those models anyway. So what we care about is being able to quickly learn. And RFDTR is really good at fine-tuning, it's really good at quickly learning. It usually gets the same accuracy after 5 epochs that YOLO gets after 50. So that is all coming from Dino V2 backbone that we base this model on. So that information is already there, you just need to access it during the fine-tuning. And yeah, that's what we did for this project. So we collected like 1,000 images from NBA games. We annotated them with bounding boxes, with different classes. So we have players, and we have their numbers. We have additional information about what the player is doing. So sometimes when the player is dribbling, we have class player in position. When the player is shooting, we have the jump shot. When the player is doing a layup or a dunk, we have the class for that. When the player is playing defense and trying to stop the offensive player, we also annotate that. We also have information about the rim and the ball, and we also have the information about whether or not the ball is in the rim, which is important as well. And yeah, this is a sample video of that fine-tuned model running on example video. And you can see that now the ball in basket appears. So we are capable of tracking those players. We are capable of detecting those numbers. We can track the ball when it's in the air, and we know also when the ball is falling into the basket. Quick segue, RFDTR is not only detection model, it's also segmentation model. You can perform real-time segmentation. We are state-of-the-art for real-time segmentation as well, and it's not yet released, but we are also doing keypoint detection. It will be released, I guess, on Monday, so it's like super preview right now. But what is interesting about our keypoint model is that usually if you work with keypoint detection models, they give you the skeleton, they give you confidence for the whole skeleton, and they give you like a single float number for every joint. But what we also give you is we give you like a spatial confidence. So we say that if the point is for some reason occluded or the footage is blurry, we give you the confidence, but we also tell you like how confident that we are that the point is here and here and here and here, and so on. So that can be useful, especially if the points are occluded and you would like to have some educated guess where that can be. And for now, we only release one checkpoint, but we'll release more checkpoints over the next week or two, I guess. And here is another QR code. This will take you to RFDTR repo. You can use the tutorials there. While you are there, you can also leave a star because my yearly bonus depends on the amount of stars that all of those repos are getting. So collectively, we can bring me closer to that goal, which would be really awesome, guys. Okay, so now we know where things are. It would be awesome to know how they move through the video. So this is one of the first demos I ever created in RoboFlow. And those of you who pay attention, you see that there are some numbers associated with the players, and those who really pay attention see that those numbers tend to change sometimes, which shouldn't be the case, because the whole idea is that we can attach the tracker ID that is consistent across the whole video. Turns out that the tracking is pretty challenging. For that demo here, I was using ByTrack, which at the moment of making that demo was like really close to state of the art. But how ByTrack works is actually only using bounding box coordinates to associate them and create those tracks. And if you only use bounding boxes, then it really depends on the quality of detections that you're getting from your detector. And if your detector produces like double detections or false positive or false negatives, what you end up having is a situation that the tracker is also making mistakes at the end, and it can swap tracks, it can kill the track that should be still alive, or it can spawn a new track where it shouldn't, so things like this happen. So that was 3 years ago. Now, computer vision is also moving fast, maybe not that fast as the language, but we get segment anything free, which is a pretty cool model because it allows you to track things through time, and you can do it in a few different ways. So here is a demo of me just prompting segment anything free with the text. So what you can do is you can give segment anything free a video and just prompt it and say, I would like to have a jet or ski or car, and we'll look for all the cars in the frame, and we'll track them through the video and give you tracking information along with that masks, which is pretty sweet. What you can also do is you can use bounding boxes to prompt segment anything free. So those of you who remember, we fine-tuned RFDTR to detect players. Now we can detect those players on the frame, and now we can use those bounding boxes to track them and to prompt some free and to track them. And that's exactly what's going to happen now. So all I did is I just gave segment any free the frames of the video and bounding boxes on the first frame, and it can do this. So it can perform segmentation across the video, attach consistent tracker ID way better than ByTrack would attach to it. So now we have segmentation and we have tracking all done in the one shot. one of the things that I didn't mention, what I do is RoboFlow is I do open source, I do those demos, but I also do tutorials. I do YouTube videos and notebooks where I show you how to use models. So if you want to learn more about segment anything free, you can just scan and that's it. And one more thing, that demo that I created was 3 years ago, and I kind of care about tracking. So we have like a dedicated project at RoboFlow called Trackers. This is the demo that we made like 2 months ago. And this is not some free, this is tracker based on the unbounding boxes. So we came a long way. You can do a lot better than I did 3 years ago. You just need to spend quite a lot of time playing with it. This is also open source project. You can also scan the code and it takes you to the GitHub. So there's that. I see some phones. That's great. Okay, let's move on. Okay, so now we know where are the players. We can track them, but we don't know who those players are. And in basketball, to know who the player is, you need to know 2 things. You need to know what team they are playing for, and you need to know what number they wear. So let's start with what team they play for. You could brute force solution to that problem. Pretty much in NBA, there are like 30 teams. Every team has away kit and home kit, but realistically speaking, most of them have like more than one set for each of those. So they have, let's assume, 2 homes, 2 aways. That would be 4 kits, 30 teams, 120 different versions of jerseys that you would need to collect and annotate. Seems like a lot of work. I'm super lazy, so I was looking for something that could work perpetuity, because the problem is that next year they will change their kits and you need to do all of that work once again, which is kind of useless. So I was looking for something that I could just apply to any footage where there are 2 teams and it should work. I created it for a different problem, for a different project, but I applied it here and it works. So what we do is we take those detections of players that we have and we crop them out. We focus our attention to like the center of that crop where the most information about the actual team they play for is visible, like for example their color of their jerseys or the shapes of their numbers or things like this, and we calculate embeddings for each of those crops. You can use models like Clip, like DynoV2, like Siglip, like I was using, and that gives you embedding for each of those crops. And theoretically speaking, embeddings should kind of like contain like a information that would be like high-level information about what we see here, and we would be able to cluster based on that. There is only one intermediate steps. I'm taking that from this high-dimensional space into 3 dimensions with UMAP library, which is something that you can use in data science. But I'm using that here, and I just use k-means, I guess, to just cluster them out into 2 teams, and here's that. And you can see that this approach kind of works. We get the correct division across 2 teams. Nice. And now I can, if I have like a really stable tracker, I can only compute that information once for the first frame, attach it to tracker ID, and I can just pursue. And here you can see we have color-coded output from SAM, but now with additional information about who is playing for which team. Now, once again, 3 years passed. That idea was created 3 years ago. So since then, we have VLMs. And there are VLMs that you can pretty much prompt to give you that information with like 0 training, 0 prior knowledge, other like fine-tuning. It has prior knowledge from the data set, I assume. So you can say, hey, here is the image. It's the first frame of that play. Give me players in white, and it will give you bounding boxes for players in white. It can get even better because it has so much knowledge about the world that is surrounding us that you can pretty much prompt it, hey, give me player playing for New York Knicks, and it knows that if the New York Knicks are playing away game, and it's away game because it's Boston Celtics home court, they play in blue with orange numbers, so it knows a lot about a lot, and you can just straight up prompt it, and it will give you those bounding boxes. You can do other things as well. You can ask for players with specific numbers. You can ask for players doing specific actions. So VLMs are pretty useful. And once again, if you have stable tracker, then you can do it for the first frame of that play, and then only attach that information to the tracker ID, and it will give you tracker ID for every frame, and you will just look it up, and that's it. So it's very easy. And also, kind of like on a sideline, but it's an interesting use case as well. So those of you who were paying attention to the data set samples that they were showing probably noticed that they only annotated players that were on the court, and that was for a reason. I wanted the model to only detect players that are on the court because I didn't want it to be bothered to filter out players that are on the bench. However, you know, stuff can change. Sometimes your client will say, hey, now I would like to detect those players on the bench. And for you, that will be a massive problem because now you need to reannotate all the data, retrain on the model, add this new setup to remove those players that are outside of the play, but include them if the customer wants that, you know. VLMs allow you to be flexible because now I can prompt for those players and can say, hey, I would like to have those unique players, but only those that are sitting on the bench, and it will give you bounding boxes for them. So that's a massive flexibility that you can use. And that model was Qwen 3VL. Since then, I guess we have like 3.5 or 3.6 VL. I'm trying to keep track of them, but it's pretty hard. So there's that. So probably it's even better. That demo was created like a half year ago or something like this. So what do we have right now? We know where on the frame, how they move, which team they play for. The last part is knowing the numbers. So that should be easy because we have our detector. We already used it to crop the players. It was working. Now we only crop the numbers. It should work as well. So turns out those numbers are super blurry, and that's a problem. So here's a quiz for you. Which number is it? Is it number 0? Hands up. Is it number 8? Is it number 9? You're wrong. That was number 8. Don't worry, it gets harder. But you can see that number quite well for some frames, but you can see it terribly for some other frames. Here's another quiz. Is it number 3? Is it number 8? Is it number 6? Is it number 9? Most of you are right. This is number 9. You can see that. How about this? Is it number 0? No, it's number 10. So the whole point of this presentation is you cannot look only once. You need to look across different frames. You need to track those players, track those numbers, keep track of what you predicted, and only then you will be able to know what number is that. So to do something like this, you either need to have like a VLM that can consume multiple frames that you acquired at different moment in time and use that for a single prediction, or have a OCR model that is super fast, and you can run it for like multiple times a second, let's say 4 times a second, probe that, and then keep track of what you got and figure it out. So there is a model like this. It's called GLM OCR. It's a VLM, but it's very small. It's like 0.6 billion parameters, which I know for like a lot of people working with detections seems like 10 times bigger than the biggest detector that they are using. But this is the reality right now. A lot of models are super big, and this is like a tiny model compared to the big models. So it's pretty cool. It also, it is like a VLM, so it produces tokens, but not like auto-regressively that every tokens is a separate kind of like forward pass. It can detect multiple tokens at the same time. So it's actually quite fast because you only need one cycle to give you the numbers versus like multiple cycles that you would typically get. So here is this model running OCR of license plates. It's doing pretty well. He is pretty tough task of extracting serial numbers from tires, which like 3 years ago was almost unsolvable. Right now it's just a single pass through the VLM, which is pretty crazy. And here is a task of reading dates from US post tags, which is pretty crazy because they have like 20 different patterns for a single country, which sounds like a pretty easy problem to solve. You don't need computer vision for that, but we do that, and it's also doing that pretty well. So here is the visualization of a play in slow motion where we use that model to extract those numbers. So what is important here is that not every number is visible at the same time, specifically not for a first frame, but also in time. Some players are with their back to the camera, some are on the side, some are doing, some are occluded because they are like very close to the opposing team player and they need to protect the basket. So generally speaking, that sums it up. You need to look multiple times through time to get as much information through time and get this like number at the end correctly. And this is a visualization of kind of like the final result. You can see that some of the numbers appear quite early. That's because the player was in a fairly favorable position when it comes to reading their numbers. Some are coming quite late because we need to wait a little bit of time to actually read that number. But in the end, we got the numbers. So now we have all we needed, and we can just look it up, yeah? So NBA gives you rosters for every game, so if you know what games was that, if you know what team is the player playing for, if you know the number, actually getting the name is fairly easy. Okay, so one of the things that we wanted to solve is solved. GLM OCR tutorial, if you want to take a look, is here. And now the question is, where are they really? Because all we know is like where they are on the video frame coming from the game footage, but that's not actually the information we would like to have. We would like to know where they are actually on the court. And to do that, we will use a little bit of like old school computer vision, which is homography, but homography requires you to have pairs of points across two different camera perspectives. So you need to have points on your source camera view and on your target camera view. So I came up with like a list of 32 characteristic points that I would like to keep track on camera frame. The problem is that you need at least 4, so you won't be able to compute that if you don't have at least 4 points visible on the frame. And if you watch football, basketball, you know that the camera pans, camera zooms, sometimes you see only like a small fraction of the court. So to be fairly sure that I always see like 4 points that I would care about, I need to come up with quite a long list of those points to be sure that even if like a tight zoom comes in, I will have at least 4 of them. And of course, for the target, it's pretty easy. We don't need any computer vision. We know how the court looks like. Those dimensions are predefined, so you can just calculate them. And yeah, here's the result of key point detection model, fine-tuned for those points. You can see those pink points are fairly stable. They could probably become more stable with more training, but it's a-okay for that particular task, so we should be fine. So now that we have those points, we can look up the same points on the target court, and we can compute homography matrix and perform transformation of any point from one camera view to another, and the other way around. That's easy. What's happening now? Well, let's see. Oh, that's great. Let's quick refresh. Sorry, guys, for that. I don't know what's happening. But yeah, in the end, when we did that, we can map their position on the court, and we can keep track on how they move and what's happening. So that's the outcome that we've been looking for. We can also, like I showed you at the very beginning, have like pretty good idea on how they moved through time, which, like I said, is pretty valuable information in basketball. And in the end, because we had the class to detect player shooting, we had the class to know whether or not the ball fell into the basket, and we did all of that key points detection, all that stuff. What we can do right now is we can detect when the player shoot the basket. We know where they were when they shoot the basket. Because we map all of that on the actual court, we know how far away they were from the basket. So that's, demo mostly for US markets, so it's in feet, but you can convert that into meters if you want. And we can map all of that and collect all of that information fairly easily. And yeah, I'm going towards an end. I have some footnotes, some things that I would like to show you, but they didn't really fit the whole narrative, but they cool enough and interesting enough that I wanted to show it to you. VLMs, like I told you, are becoming quite an important thing. And I think FIFA will use it quite soon to identify whether or not a given situation was a foul, whether or not it was red card, whether or not that was yellow card. There was a competition on CVPR, which is a conference for computer vision, last year, where they did exactly this. The winning solution was VLM. This year, people from FIFA were there, so it seems pretty kind of like obvious where it's all going. Quite soon the referee will be just there to tell you it's a yellow card because the decision was made actually somewhere else. Speaking of decision made totally somewhere else, the whole VAR, it's also a computer vision solution, is actually multi-camera, multi-skeleton, 3D pose estimation. So what they do is they have like 16 cameras in the stadium. They keep track of the plays, and they just use computer vision to figure out where the skeletons for each of those players are located, and they use that to figure out whether or not it was offside or not. Whether or not it works, it's debatable, but it is what it is. Interestingly, we are slowly moving towards the direction where you will no longer need multiple cameras. There are already models that can do a single frame, single camera, multi-pose pose estimation and locate all of that in 3D space. That's another crazy direction that we are going. And that would make VAR a lot more accessible if that would be the case, because right now it's very expensive and only, can only afford that and for selected games, for selected teams. And it, requires quite a lot of GPUs to actually execute that over there. So that should make it a lot more interesting. And last thing that I wanted to show you, this is literally coming from like 2 days ago. So apparently DeepMind is working with some Premier League teams to come up with like graph models to model the football pitch and how things are happening. And they can look 8 seconds into the future. So imagine that if they can look 8 seconds in the future, the betting game online is becoming a little bit rigged because they know the future, you don't. So that must be interesting to be there. DeepMind is looking for funding apparently, and they decided to rig online betting. That's it. Thank you very much. I'm sorry I was speaking so fast. I had like 90 slides and I needed to power through it, but I still hope you understood what I was talking about. Yeah.
Thank you very much for the talk. Any questions?
First of all, thank you so much for the talk, very interesting. I'm referring to the part where you were using Quen to do a text prompt. What about you have a visual prompt, like you have external images, you want to referential few shots or only one shot. I just play a little bit with the Sun3, which is not a VLM, but it's more a prompt concept segmentation model. And I found quite hard if you have an external image you want to transfer that like an embedding. You can only play on with positive or negative in the frame itself. What is your advice?
I mean, with Sun3, I guess theoretically speaking, you can't do cross-image referring. You need to hack it a little bit. Kind of like stack together the source image that you want to have and the target image, because it can only work in like a single image context. So you need to play from the very beginning. You are doing some crazy thing to get it to work. But there are some models like I'm working for RoboFlow, so I will refer to what we have. So we have a feature in product that is built on all V2 model, and that allows us to do exactly this. So we have a way to allow you to annotate only like 5 images, and we will propagate this kind of like concept of this thing across the frames, and we can also do negative and positive bounding boxes. And you can do multiple examples because of that, because you can do, I believe, do up to 5. But all itself doesn't, I guess, limit that. It was just our like choice in the UI to make it more understandable to the user. So yeah, that's the model that I definitely know about. But there are for sure other open source models that can execute that better than, I mean, better, easier than some, yeah, because with some it's just, you need to hack it to make it to do that. Any more questions?
Other questions?
A concept throughout the presentation was the fact that in order to do that, you need a stable tracker. But as you mentioned, you may have zoom in, zoom out. You may just have times where you lose track. So I'm guessing these also have some part of re-identification. Do you do it only with the numbers, or do you also play around with other sort of re-identification?
So some free advertises that they can do re-identification. If you try to do it, they don't have it, the re-identification. But from what I heard, they want to have it. So that's it. But yeah, there are other solutions. I mean, first of all, there are other papers and other models that we're building on top of some free that improve their re-identification. So you could, theoretically speaking, still have one model and get that re-ID a little bit better. For cases like basketball or football, it might work, yeah, because you still have like limited amount of players. Like if you want, if you watch a game, you know, it's usually like 1 or 2 players are outside of the frame and they come back. So that could work. But for a general solution where, I don't know, you have street and you would like to know whether or not it's the same person or not, that will not work. And to be honest with you, I played with a lot of re-identification libraries, and most of them are just lying that it works. There is like fast re-ID. Yeah, it's just not happening. So for this one, we use numbers. Yeah, so if I reacquired new track, I don't have number attached to it. I collect that information about the number. That's the same number. I'm stitching them. You can do other solutions, like, you know, like a quite advanced state where you know that the person left and you know from which side, and you can predict, you know, you can do things like this. You can do camera correction where you actually kind of like subtract the camera movement and only keep the movement of the person. So theoretically speaking, it's still there and you can reattach that on a different level. So there's that. I use numbers because in my experience that re-ID didn't work. Didn't really work.
Any other question? Don't be shy. We still have time.
Guys, it was a cool presentation. Definitely you have some questions. If you don't, we can talk later. That's fine.
Okay.
So with homography, you need to make the assumption that the feet are touching the ground, right?
Yes, I mean, I removed slides about it, but I can show them if you want. So the thing is, yes, the whole homography concept is, this is the slide that I want to show you. So can I, probably I need to unhide it, yeah, to make it large. So the question is about, hey, it only works when the player is touching the ground. That's correct, which is a little bit unfortunate because in basketball, hi Francesco, everybody is jumping. So that's what you get when the player is jumping. And so the orange, you don't see that. Can we for a second bring my screen back? I'm so happy because I removed that slide because I was in a hurry and I was like, maybe we'll skip this, but okay. So what's happening, this orange guy will get the ball. 2 things are happening. One, he will go past the referee with, Jesus, sorry. Oh, where are we? Okay, bear with me, I'm sorry. Okay, we are back. So 2 things will happen. He will pass by the referee right now. What will happen is, because of how object detection works, his bounding box will shrink. It's almost like he jumped. So it's no longer touching the ground in the place where he is touching the ground, and you can immediately see that in the projection of his movement. He's back, and now he's jumping. Also, the model thinks that he moved where he actually didn't. So I have another slides that I could also unhide, probably multiple of them at the same time, if that's possible. And yeah, so this is the trajectory, original trajectory. And you can do a little bit of like old school machine learning signal processing to kind of like look for the actual signal and detect the noise in there. You know, it's a very small sample, so depending on your like settings and coefficients that you will set, you can kind of like tone it down and make it look a little bit more like the actual movement. But yeah, that's the minus of homography. If somebody is jumping, if somebody is not touching the ground, then that is no longer a correct information, and you need to apply post-processing, which is, in my opinion, like in my case, what was signal processing approaches to remove the noise. More? We are already 40 minutes, but I'm open with more questions, but I don't want to screw up the whole timeline here. So.
We still have a couple of minutes while you are, of course, rating the talks, if we have the QR back.
While you are rating the talks.
Here?
How can you understand if in a basketball match, if a player is touching the ground, since the matrix is two-dimensional?
Mm-hmm. Yeah, so how can I do that? Usually by that signal processing. So I don't really know he touched the ground. What I can detect is something that is very unusual, because if he jumps, how the perspective projection works is depending on the camera angle, that will move his position by several meters in like split of a second, which is totally unusual movement. And you can use those methods that I talked to you about to set kind of like a reasonable movement that makes sense, yeah?
Are these algorithms based on a Kalman filter?
Those for signal processing? Yeah. Some of them are, but the one that I used was not. But if you ask me exactly, I would need to check, because that demo was like 6 months ago. But yeah, some of them, yes.
Last question.
Very quick about this. How about
the most interesting part of the talk apparently is the one that I removed. Yeah, okay.
How about the ball that is always flying up and down? How do you?
This is even more interesting, guys. So first of all, in basketball, once again, okay, so generally you get how the basketball look like. First of all, the problem is the ball is almost constantly above the ground. I just need like a video, yeah, that was pretty cool video, so you can use it, yeah? So here even, okay, so let's, I'm using space. So here the ball is here. First of all, in basketball, ball is very often completely occluded. You don't even know where it is. So that's the first problem. Then, even if it's not occluded, like right now, maybe right now, it's actually above the ground. So even if I will detect that ball, homography will not work. Yeah, and when it's traveling usually through the air. Once again, homography will not work. So, first problem is you need to detect the ball reliably. It is a problem. If you use just the detection, that's why I didn't include in that. I tried that and it didn't work. Object detection is not good enough. You need something better. There are, for example, approaches during the CVPR. They applied it in football, but I think it's applicable also in basketball. So what they did, they didn't track the ball at all. What they did is they track players, where they look, and figure out where the ball is based on movement of the players. Because it's actually, if you can track that reliably, that's a much better information, because it's hard for us to get all those players occluded, and typically most of those players will be looking into direction where the ball is and kind of like move in such a way to either be on a good shooting position or be in a good defensive position. So ball actually dictates all of that. Where is the ball dictates how the player are moving. So I didn't do that, but I think it's a pretty cool idea, and I would try to use it. And another one is, and that's already we kind of like thought about it. If you would know where the players are and where the ball is, I would just assume because ball is either in their hands or they dribbling it, or it's moving between them or to the basket. So I wouldn't even try to use homography to kind of like map the position from the frame to the actual map. I would just figure out whether or not it is currently in position of some player, and if that's the case, I would assign the ball to the position of that player. And if it's not, I would just look for the next event when that would be the case, and then I would backfill with just like linear interpolation to fill that gap. Yeah, but that's another really cool question. Yeah, thank you.
Another one. We have still time for another one.
Thank you for your presentation. Do you have some advices for deployment of VL model on constrained hardware like Jetson?
Yeah. That's a problem. That's a problem that we are facing as well. Yeah, some of them you just won't be able to deploy, obviously, because it's just impossible. That's why I showed you like GLM OCR, because that's a model that is for sure deployable on Jetsons because we did that. Of course, like quantization, things like this. That's we're like, limiting the floating point precision. But obviously, you will lose quality with that. You can also use smaller model and just try to distill the knowledge from the larger model to the smaller model. That works well for like limited tasks. So if you would like super focus on like tasks that you need that. Let's say, let's use this OCR. Yeah, so if you would only fine tune for like specific subset and only for specific task, then you could probably get away with a lot smaller model, still keeping quite a good performance. But I'm also probably not the best person to ask that question, so I'm just guessing. Yeah.
Very last one before going.
So how much harder would it be to map everything to a 3D model? Instead of having a 2D model of where everything is, have a 3D coordinate system, potentially with multi-camera data if the NBA makes that available?
Mm-hmm. So I only can guess, because it also depends on the amount of streams that you have, etc. There was another paper on CVPR this year called MAMA, M-A-M-M-A, and that was a model that was pretty much attempting to do that. They had like 4 cameras, no more, nothing more than only those 4 cameras, and they wanted to recreate everything in the 3D space with 3D models. So I didn't try it yet, but I have a friend who tried it. They use 4 iPhones to capture the footage, and it took him 30 minutes to process 1-minute video. But the quality of that 3D was exceptional. So it was comparable to like those suits that you use in the gaming industry, because that was the whole pitch for that paper, is that you no longer need that because it's so accurate. So at least in his test with 4 iPhones, but only 1 person, it was working great. They only they also advertised it should work with multi-person. So that's all I can tell you, because the CVPR finished few days ago and I still haven't had time to do that. But I really want to do like a demo with 4 iPhones and try to do it. But Mama apparently can solve that, but it's slow. But it runs on a single GPU.
Thank you very much, Piotr, for everything. Remember to rate the talks and to